There's a block. Now, what is the time period of oscillations of this, or what you can call angular frequency of oscillation omega naught, which is k by m. Here, absence of any air or no viscous drag. We'll write it here. No, in the absence of air, then no viscous drag will be acting. Then the angular frequency of oscillation is given by under root of k by m. I think that this is no problem. And what is the equation of motion? So in fact, what is the idea? The idea will be kx naught plus x. This will be mg. Initially at equilibrium, I further pull it down and release, then it will accelerate. Then the equation, what we write it, minus ma equal to kx naught plus x minus mg. And we know at equilibrium, kx naught equal to mg. Assuming that you know all these things, directly I'm writing it. So kx naught will cancel out. So what is the restoring force? Minus ma equal to kx. Or further, this will be written as minus m d square x by dt square. No? Or what is the equation it will be? So this is the equation of the SHM. Further, we'll write omega square equal to omega naught square equal to km. Then solving this, we are getting this equation. I'll write in step. There's a background what we know. And what is the angular frequency? Under root of k by m. Okay, there's the expression for angular frequency of oscillations. So shall we call this as like a undamped? I'll call this as like undamped because there is no any other forces acting other than restoring force of the spring. So what is this? Everything what we are discussing is an undamped oscillation. Let me immerse this in a liquid. So this spring block system, what I'll do is like, I will take this. This everywhere liquid is there. Okay, here liquid is present. We know example of liquid, water. What is the best example? It will have viscous drag. Now what will happen? We'll see it. So initially it is in equilibrium. Again, you check it. No, the books, what happened, everything is fine. That's a small basic diagrams. What actually it is? What do you mean by damped oscillation? Where do we see that? That's a small basic things. What happen? Maybe the textbooks they have discussed as if that there's a very general thing where no need to draw diagram. No need to draw diagram. In that way, what happened? They just started with mathematical treatment. So what are the forces that are acting? Kx naught, mg, and there's a bind force. Will I agree this? So initially, what is the elongation of spring? Let it be x naught. Now I'm going to further stretch this. Oh, no, anything will happen. So consider the viscous drag also into the picture. Tell me what will happen here. How you write now? the equation of SHM for this. Okay, I'll just modify the diagram. I thought, okay, no. What are they still? What are the forces acting? Mg. It got further elongated. X. So how much of spring force here? No. Further, it is being elongated. So spring force, how much will act? K x naught plus x. Then along with that, buoyant force. So I'll give velocity at this particular point. Okay, better. So yeah, when it arrives here, it will have velocity v. At mean position, I'll give velocity v naught. Then the block starts moving down. Then viscous drag, water will exert viscous force. So viscous drag will be acting. And along with that, a buoyant force will be acting. What are the equations we can write here now? I think initially FB plus KX naught will balance mg. So initially FB plus KX naught equal to mg. So now what is the additional force that will be acting? So minus me. So in what direction the retardation? The retardation will be in this direction. So therefore the equations of motion will be minus me is equal to minus, also like a FB will agree this. Look at all the equations. The resultant force FB plus spring force Kx naught plus x plus viscous drag minus mg equal to 0. There's a retardation. So we know from here initial FB plus Kx naught minus mg should be equal to 0. So what will be left over? Will be left over with Kx plus viscous drag. So this will be, we'll be writing it as, what is viscous drag? This entire viscous drag, I'll write it as B into V, where B is called as damping coefficient and depends on so what all, I think you go back to depends on shape of the body, the shape of the body and nature of liquid. So this particular damping coefficient, it depends on what all? Damping coefficient depends on shape of the body and nature of the liquid. Water, I'll take oil, I'll take honey, milk, let it be different types of liquid. For different types of liquid, this damping coefficient will be different. So if you may get confused, sir, what is that? Just very simple. You go for viscous drag. What you write? 6 pi eta. This is for spherical ball, no? What is eta? Eta depends on nature of liquid. And instead of this, if you take a cylindrical shape, the body instead of spherical, if the cylindrical shape, some other value will come for this. This will be some other value. If it is some cubical block, what will happen to this quantity? 6 pi r will be different. For different shaped objects, again, this quantity will be different. Again, for different liquids here. So therefore, the damping coefficient depends on, B is a damping coefficient, depends on shape of the body, shape of the body and nature of the liquid surrounding the body. Okay, water, or I'll write better liquid. Nature of a fluid, even it can be gases also, water be that one. So for different shaped objects from viscosity chapter, we know that this particular formula is applicable only for what? Spherical. If I bring cylindrical, cubical, conical, definitely this formula will change. So that everything will call that as damping coefficient. Okay, fine. So nothing big. Already we know viscosity. This is a viscous drag. So what is Fe? Fe is a viscous drag. This is a small thing which will help you a lot. No, you can understand this particular question very easily. So what is the damped oscillation? We are discussing now the oscillations in the presence of some resistive force like a friction. Here it's a viscous drag where the viscous drag will be proportional to V. So that SHM along with some resistive forces is what damped oscillation. This was practically, yeah, what all we discussed till now it's a theoretical. This was the practical. Okay, this particular we can rewrite this as minus M. Okay, this is the equation which is little bit difficult, no? The what we have seen. Okay, plus it is. What the equation we have seen and the what equation you have is little bit different, no? This is an additional parameter it has come. Without this, it will become SHM, what we have studied. No, some damping effect has to be introduced here. So we have to solve it. If you solve this, what is the equation of SHM will be? If you solve this particular thing, what is the solution for this? It will become A sine omega t plus phi. General solution for this equation when you solve it, no, I think if you have studied in calculus, if you integrate this and solve it, no, the general solution for this will be this much. What is x? X will vary harmonically. This is undamped oscillation. Now for damped oscillation, okay, this additional parameter, what we got it. So when I solve this, the general solution for this will be x is equal to a of t cos omega t plus pi. You need not to bother, sir, how it has come directly. Uh, Solving the second order differential equation with some constant. So when you solve it, no, we'll end up this equation. So even in maths, I think you don't study. Okay, you can just leave it on this one. You can remember here. So here, if there is no damping effect, then the general solution for the second order differential equation is this much here. Sir, why you write sine cos? It all depends upon the phase angle. I'm not saying that it should be sine only. Whether it's a sine cos, it all depends upon the initial phase. Agreed? Similarly, here also that one. What is this? The amplitude. That amplitude varies with the time given by A of t equal to A naught. I think I'll magnify it. We'll minimize it so that we'll get some space here. Okay, the general solution for this will be A of t equal to A naught e to power of minus bt by 2m. Don't bother about how it came. If you refer some books, no, related to oscillations and waves, there it is being derived. So as far as our level is concerned, we'll just accept this one. So what is B again? B is the damping coefficient. What is M? Mass of the block. Agreed? No? See, like I want you to look at the picture. In the picture, so like the value of B depends on what? Will it depends on spring constant? No. It depends on what? It depends upon the nature of liquid. Okay, this is. So this amplitude, it will vary with the time. And then what about the omega? Omega is given by the formula omega naught square B by 2m. What is omega naught? Already in the previous section we have discussed. So this will become K by M 4m square. So this is the angular frequency. What is tan phi? Tan phi also let me define. Tan phi depends upon B omega So you look at the mains exam, no, they just asked what is the phase angle. It depends upon the value of these things. The phase, this particular thing. What is the amplitude? So this is the amplitude. It will vary as a function of time. What is the oscillation energy? Okay, now we know oscillation energy is equal to oscillation energy will be, it is called as E of t. We'll try to get, we know amplitude. So what is the oscillation energy? Oscillation energy should be equal to, how much? It should be equal to E of t should be equal to K. Like in SHM, we used to write K square by 2. So this will become, I'll square that quantity, A naught square by 2, E to power of minus BT by, okay, this after solving, K A naught square by 2 E to power of minus BT by M. This is the expression for the energy. So this K A naught square by 2, I'll write it as E naught here. Formulas are very, very, very important. Okay, this is about, so, so these are the equations what I had. Still students asking, sir, where do we use? This is what practically we see. Till now, what all we studied SHM, it's a ideal on paper. Practically, this is the SHM what you notice. Are you getting now? The SHM now what I derived equation, no, this is the practical one. No? Practically, this is the type of SHM is what we see. What all we discussed till now, it's an ideal. We just assume that there's no viscous drag, there's no frictional force. Is it possible? Is it possible? Nothing, no. So can we do experiment in the absence of air? Not advisable, no. So practically what happens? There'll be air, and then when a block, spring block is oscillating, there'll be an air. Due to air, what will happen? There'll be an SHM. There'll be a damped oscillation. Getting some idea? Okay, now what all we discussed, I think just only straight away the set of formulas is what you have to remember. Nothing big. Everything is visible. This is what we have discussed till now. Okay, what about the type of any, sir? I'll vary the value of B because I can vary, instead of water, let me take milk. As a, anybody? Somebody was asking. Okay, I'll continue then. So what is that ET? What is ET? What is E naught? Oscillation energy at time t, and what is E naught? E naught is initial energy. Let me define these terms. What is, because every quantity we should know this one. What is ET? Oscillation energy at time t. What is E naught? With the time, what will happen to this energy? No, will it remain constant or will it increase or decrease? Anybody wants to answer? Oscillation energy. You know mathematics. I just want students to really analyze once. With the time, what will happen to oscillation energy? Will it remain constant or will it decrease with the time?
Decreases, sir.
it decreases time. This is the idea of the problem. Huh? So what all we are discussing our theory, no, this is the question is what we have to ask. Okay, damped oscillation, what will happen? The oscillation energy itself will decrease with the time. Okay, now you have to ask questions. What is that omega? Omega is the angular frequency of oscillation. Sir, already we have omega naught s. The in damped oscillation, the angular frequency of oscillation is given by this particular formula. If damping is very small, it will become omega equal to under root of k by m. If damping effect will come, the angular frequency, the new angular frequency is given by this particular formula. Able to get this, and this amplitude, you get this amplitude curve. This amplitude itself will vary. Can you expect the curve, the amplitude will vary with the time? So no. So definitely what happen? The value of B will determine how do that amplitude will vary, how that amplitude will vary. So now let me go for the plotting of graphs. Looking at these equations, no, I'm interested to know that how that amplitude varies with the time. Let me introduce to the graphs. Okay, what are the equations? We know amplitude is equal to a naught e to power of minus bt by 2m. This is